And assume this is problem yours. Face. Actually, this is a good question, so nice time. So this is your face, right? The image. Let's say that this is, let's make it easy, 200 by 100 pixels, right? So that means there are 100 dots in this direction and 200 dots in this direction, right? So, and if I take the first one, 100, cascade to the second one, and get a vector. So this is going to be what? 20,000 by one vector, right? That's not necessarily features. Okay? I'm not getting that problem. So then I get that and put as the first column right here, right? That's the first column of the matrix. I have another picture of yours, or let's say that this is facial expression recognition problem. Okay, that's a smiley face, right? And then I get, let's say, 5,000 smiley faces, and each one is a column vector here, right? Then I have 5,000 angry faces, and then I have another 5,000, right? So basically, you create a data vector, data matrix. This data matrix, let's make it up. We know for sure how many columns, how many rows do we have? 20,000. Multiplied by the number of samples. Let's say 60,000 samples, right? So that's your data matrix. Huge. You don't want to work with this. You want to do something about it, okay? In fact, experimentally, we can show that even though this is 20,000 dimensional space, the features of your face comes from a 9-dimensional subspace, actually. So there's no reason to work in 20,000 dimensional space. But by only knowing data, now I forget the problem. I forget the problem because I converted my problem to a matrix, right? My data is a matrix right now. So forget about this. All I have is a matrix. All I have is a matrix of 20,000 by 60,000. Now I have to do something with this, right? The first thing is, what is the intrinsic dimension of the data? Then, as Tim explained, I'm going to do SVD, right? U sigma V transpose. I decompose this matrix into 3 sub-matrices. Not sub-matrices, 3 matrices, product of 3 matrices. When I look at this, I will see, forget about U, focus on sigma. You will have numbers here, 15, 12, blah, blah, let's say 8, and then 0.02, 0.01, and so on. So singular values will be on the diagonal of sigma, okay? And there are 20,000 singular values. But you will notice one thing. You will say after singular value 9, there is a dramatic, sharp decrease. So, oh, okay, I have 20,000 singular values, but there is a sharp decrease after singular value 9, right? That means this data lives in 9-dimensional subspace. I don't need to worry about 20,000. Now I'm going to do approximation that Tim says. I don't want to deal with this. I do rank 9 approximation. Do you get it? So what does it mean? It is so simple. All you have to do is, I will say, well, those markers are not. Let's see. Yeah. So far you guys are with me? Very important, right? 9. It could have been 16. We don't. So you find that number, magic number. Then you say, hey, I don't want to deal with W anymore. I want to have a naive W bar, okay? And this W will be this. 9 by 60,000. Do you understand? Instead of 20 by 60,000, I will say 9 by 60,000, and I don't lose much. The variation of data, the variation of the columns is kept the same, almost the same, right? So what is it? Then you will say, hey, I'm going to do this. I'm going to get first 9 columns of U. I will say U bar. U1 all the way to U9. You see, I skip the rest. I don't care about it. You guys are with me? And then for sigma, I will get only 9 sigma values. I will ignore the rest. The same thing I will do for V. That's it. That's PCA. You did PCA actually. Okay, so then you say U bar, sigma bar. So that means now you projected your data from 20,000 all the way to 9-dimensional space. Isn't it nice? So that's SVD, right? Do you get the idea? I'm going to explain on the slides, but that's the main idea, yes. Well, for facial expression, it is 9, but there are other problems. For example, for motion segmentation, also it is 9. So you don't even need to worry about it. Give me any data matrix, I will tell you what that magic number is by looking at the rank. So this is called rank estimation. You see, even though it is full rank, there are 20,000, but I know that there's a sharp decline here. So those are due to noise or due to some other factors, okay? So you focus on first 9 dimension, yes. The redundancy in the columns, because some columns are extremely, variation of the columns are kept intact, so you get rid of the dimensions, yes. Yes. Well, there are rank estimation techniques. I simplify things, okay? So when I look at it, yeah, that's simple, right? But sometimes visually you cannot do it. But there is rank estimation techniques, and in fact, we developed one innovative one before. So you use one of those rank estimation techniques. So that will tell you this, okay? I can give you other examples. So another example is this. Any other questions? Yes. Right. Okay, very good. What? That's very good. Good question. So let's make up some data here. Okay. Let's assume that this is our data. I'm gonna do this. 1, 2, 3, 2, 4, 6, right? 3, 6, 9. What is the rank of this matrix? 1, right? Twice and 3 times. So rank is 1. Everybody's okay with that? So I'll put it here. Rank of W is 1. So when I do SVD, I will have this. U sigma V transpose, right? But I know there's only one non-singular value. So that diagonal thing, sorry about the markers, but U, this will be something non-zero, 0, 0, okay? So when you do SVD, you will have a non-zero term here, and then you will have 2 zeros. By looking only SVD, you can say rank is 1, because there's only one non-zero singular value. Do you agree? But let's put some noise here. Let's Gaussian noise, Gaussian distributed noise, or any kind of distributed noise. But let's do Gaussian. Gaussian, remember L2 norm I mentioned? This is very good for SVD, because SVD will eliminate L2-based noises. Maybe I should. Are you familiar with distributions from statistics? Yes. All right, okay. So there are 2 kinds of noises, like multiple, but this is like low tail, right? And this is higher tail distributions. Low tail, higher tail. low tail is like negative x squared. This is x. This is lower tail because that decays with the term x squared. This is higher tail because this decays with only term x, right? So Gaussian noise is this kind of distribution. For example, Laplacian noise is this kind of distribution. In real life, noise is like the image that we take and there's a noise, right? That's Gaussian. But there are certain distributions, like the missile defense system. The missile is behaving very erratically, right? So that is Laplacian distribution. But let's assume we have Gaussian distribution added to this. Let's say 0.01, 1.98, 3.01. No, this is too much. 0.5, 3.99. You get the idea, right? So I added noise. Bum. This will be full rank. This will be a number. Let's put it here, 3.5. Even though, and these are going to be 0.2, 0.01 maybe. Okay? All of a sudden that's full rank, right? But what do you see? I mean, come on, 3.5 all the way, it declines sharply, right? So that means those two are due to noise. Now I will say, hey, forget about this. Now I'm going to have an approximation, let's call W star. And in this one, I'm going to get, what I'm going to do is, I'm going to get the first column of U, U1, and then I will get only 3.5, and then the first row of V, V1 transpose. Do you understand? Why one? Because there's only one non-zero, right? Get only one column of U, one row of V transpose, and create this guy, right? This one is closest approximation of this in terms of least square approximation. Do you get it? So you eliminated the Gaussian noise as much as theoretically possible. So you see how useful SVD is. So you start with a data matrix, get rid of redundancy or get rid of noise, and also try to determine the subspace and project it into that subspace and work with lower dimensional space. Got it? So I'll go very fast with the, because I already explained this. This is nice. All right. Okay. So here, okay, this is, I'm glad you asked the question, okay? So think about the facial expression. So we have one image. This is 20 by, yes. Oh, share, okay. You see, things are so simple, aren't they? All right. So assume this is 20 by 30 image. Let's make life simpler. So each image is a 600 dimensional vector. Everybody agrees, right? So my face image lives in R600, which is huge. Think about 1,000 by 1,000 image, and this is color image 1,000 times 1,000 times 3. That's huge, a couple of million dimensions. But let's say that this is, let's make life simple. All right. And then I have those 6 images. So that means I have 6 vectors, and each one is 600 dimensional. So my data matrix, what is the dimension of my data matrix for this simple? 600 by 6. Right? I mean, yeah. So, but experimentally, it is shown that even though those 6 data points live in 600 dimensional space, they lie in a 9-dimensional subspace. Remember in R2, we had a line, 1-dimensional, or a plane, 2-dimensional. You cannot visualize 600 dimension. But similarly, that's a subspace of 9 dimension. That means you need 9 basis vectors. Do you agree? You don't need 600 basis vectors. You need only 9 basis vectors. Okay? So another problem, which I worked before, is motion segmentation problem. Think about this car. And you are taking a live video of a car, and there are 2 cars moving around. How do you determine how many motions are in the video? Like one car is moving this direction, another one's moving this direction, right? There are 2 motions, right? How do you determine? That's the motion segmentation problem. Think about this, okay? What I do is, let's assume we are looking from very, very top. Instead of three-dimensional, we'll look at the car as two-dimensional. Let's make life simple. And those are the feature points on the car. For example, yellow is a one feature point. That means this is frame one, the first picture in the video, okay? And I have 4 feature points. And these x1, y1 are the coordinates in the first frame. So you see this one here, little one. That means this is first frame. And how many feature points do I have? 4. And this is the second frame. And the second, you see those little 2, these are second frame. And I am tracking those feature points. Do you see that? Yellow went from that to that position and so on. Assume that I have F frames. You see the capital F right there? Let's say that I have 500 frames, for example. That means I'm tracking the point from each frame to, in a video, typically we have 30 frames per second. If I'm tracking for 10 seconds, it is 300 frames anyway, right? So assume that I put the coordinates like this. What does this guy tell you? X1, Y1, that means the coordinates of the first feature point in frame 1, right? And then the coordinates of the first feature point in frame 2, right? And the coordinates of first feature point in frame F, right? Isn't it like the trajectory of that feature point? So the trajectory of that feature point lives in R2F because each coordinate is 2 points, right? So that means if I am tracking for 500 frames, that trajectory lives in 1,000-dimensional space. You agree? Yes. So I do the same thing for the other feature points. You see? So I'm tracking only 4, right? But in real video, we track many, right? So here, each feature point that I'm tracking on this video is R2F dimensional, right? But we can theoretically show that even though my data lives in R2F, it comes from 4-dimensional subspace. I don't need to worry about 1,000 dimension, right? I need to worry about that 4 dimension. So, but how do I know what is the size of dimension? In your case, yeah, sure, yeah. Then you need to transpose things. Yeah. Typically I like this notation. The column is my data, but I know that row is typically a record, right? Yeah, but you're right. But this is the notation that I picked to use. So what do? What is the goal of principal component analysis? Well, keep the variance of data as much as possible, like similar in the high dimension, but project into the low dimension. So if 2 points are away in high dimension, they will be still away in low dimension, okay? So you keep that distance concept in data when you project it. Everybody's with me? So that's again, simple. That's simple linear algebra. I know we may get you confused with little stuff, but very simple linear algebra. So basically here, what I'm trying to do. As Tim explained, this is skinny version. You have matrix A, that's our W, right? A is our W, basically. And all you need to do is, if you know the rank is R, if you already know it, okay, then say U sigma V transpose. That's the exact representation or exact decomposition of your matrix. Okay? Because you know rank is R. If the rank is R, but if you are taking only K, that means there's rank K approximation. Let's say the rank is 20, but you're taking only 11 singular values. You are approximating your matrix with R1, 11. Rank 11 approximation, okay? Rank 20 approximation is itself, right? Because you already, so now all you have to do is, but even before that, let me explain this. Here are your data points, right? So what is the goal? Look, do you see that it comes from a line actually? But because of noise, it deviates, right? So it is in R2. Our vector space is R2, right? But well, it comes from a line. That means it comes from one-dimensional subspace. So how am I going to find it? That's my question. So I can do it many different ways. One is I'm going to find the line which is the best line. In what sense? If I look at the distance between each data point and line, if I add them up, I'm going to find the line that will minimize it. Do you understand? So that's called least square. Why is it least square? If it is 2, actually. If I look at the distance between a point and the line, get the square of it, add the squares, and then get square root of, like L2 norm. This square is nothing but L2 norm, guys, okay? So, approximation. So this is what it is. Now when I look at here, you see, I look at the distance between each point and line. That is the closest one is what? 90 degrees, right? Okay. How about if the data is in 3-dimension? Look here. It seems like even though the data lives in 3-dimension, it comes from a plane, right? So I'm going to find the best approximation of that plane with PCA. Okay. So here it is. The goal is, guys, we have n by p. N is the dimension of data, right? The data lives in Rn, and p is the number of data points. Do you agree? So I have p number of data points. Each one is n dimensional. That's my original data. I don't want to work with Rn. If possible, I want to work in another dimension, k dimension. You see, from n times p, I want to go to k times p. Instead of Rn, I want to work in Rk. Well, what is k? Right? You don't want to have k2 because you may lose a lot. You don't want to have k 500 because that defeats the purpose. So what is the best k? Who is going to tell me what is the best k? How can I find the best k? Rank, exactly, or SVD. You do rank. But how do I find the rank? So in order to approximate the rank, first do SVD, look at the singular values. When there's a sharp decline, bump, cut it there. I'm making life simpler for you guys. It's a little complex, more complex than that. But basically do SVD, look at all the singular values that Tim explained, and then find where it is, there's a drop, bump, that's your key, K, sorry. Key and K, yes. Well, if the rank is 9 and 15, I always do 15 to be on the safe side. Okay? Yeah, you can do, but still, from 1,000 to 15 is a good deal, right? Are you with me now? So now we did find the K, right? Do SVD, look at the singular values K. Okay, now you know redundancy. You don't want to work in N. But now how am I going to convert my W into W bar? That's the next question, right? So that's easy too. I'm telling you, all those are fun and easy. Very easy. Thank you, Tim. All right. Actually, it is right. I'm going to talk to you one thing. All right. So let's say that we have a vector x. This is vector x, right? This is a vector x, and then I have a vector u. What is the projection of x on u? Okay, that's the notation I use. When I say projection of x, all right, on u, what does it mean? Projection. Projection means I'm going to project it, right? That's it. This vector right here is projection of x on u. Do you agree? Very good. And let's say that this is theta. Okay. Then I will also put it here so you can see too. Okay. What is this distance right here? That is the length of x times cosine theta. Is that right? Okay. So that's the length. If I find the unit vector here, like if the unit vector is length 1, what is this unit vector here? Isn't it u divided by length of u? Like u is, let's say, a big vector. If I divide it by the length, I will find a vector in the same direction of u, but length 1, right? If I multiply this by u, do I lose it? That means projection of x on u as a vector. Everybody agrees? Very good. Then, what if I do this? X, okay, and I multiply this side, okay. I multiply u. Should I, I'm gonna use, anyway, let's be consistent in math. U cosine theta times u divided by u squared. Is that right? I'm going to multiply both sides with u, length of u. Do I lose anything? No. All right. So this guy, if you remember in the early morning, this is nothing but u times x, inner product of u and x. Okay. In other words, it is the inner product of x and u was u transpose x or x transpose u. They are exactly the same thing. Remember? If you don't remember, I'm just telling you, okay? So inner product of two vectors, u transpose x or x transpose u. They're exactly the same thing, okay? And basically, what I do here is, let's see, what can I do here? Okay. U transpose x, u divided by u squared. Is that right? Huh? See, this is like inner product of u and x, right? Well, I'm going to switch that. I will say, hey, I will make this, because this is vector, this is scalar. Is that right? Can I switch places? So can I say u, then u transpose x divided by u squared? I don't lose anything, right? But let's assume, if we assume that u is already size 1, if the u is already unit vector, like then I can get rid of this, right? Assume we are starting with the length 1 vector. Then this becomes u transpose x, right? That's it. Projection of x on vector u is u transpose x. Do you agree now? Okay, so this is getting really interesting right now. So you see, this is a number. Do you agree? This is just a number. But this is a vector, right? So let's say this is 5. That is 5 times u. So basically, I'm expressing x in terms of u in some sense. Do you agree? Because isn't it the same? I mean, I am expressing x in terms of multiples of u when I project, right? Keep this in mind. Okay. Now, I'm going to make this, don't forget this. This is u transpose x. Don't forget it. Now, I'm going to make it, instead of projecting a line or a vector in onto another vector, I'm going to project a vector on a subspace. Because that line was a subspace anyway, right? But it was only one dimension. What if I'm projecting into multiple dimensional subspace? So that becomes interesting, but again, very, very easy. So assume that I am projecting my x onto a subspace whose columns onto a subspace, right? But how do I define a subspace? With its basis vectors, do you agree? For example, when I say this is the plane, I can get two vectors, and any point in this plane can be represented as linear combination of those two, right? So what I'm going to do here is projecting vector x on vector u was u transpose x. But now I'm going to project onto u transpose x. And u is whose columns are the basis vector for the subspace. Do you understand? In fact, this U is just a one vector, right? But here, if there are two basis vectors for the subspace, I will put them in the column. That's exactly the same. So now, let's be practical and show you an example. I know we are almost out of time. So I'll go with that. Okay, so this is what you're going to do. You're going to start with Wn by P. Rn, P data vectors, right? Okay. Then you're going to do SVD, U sigma V transpose. And if you are projecting in k-dimensional subspace, you get what? The first k columns of U. You see that? U tilde is the first columns of what? U. And then all you need to do is you are going to get your data, each column of your data matrix W. And you are going to project, this X is one column of W, okay? Get each column of W and project it into U tilde transpose. Again, let's be practical example and you will fully understand this, I promise. And similar to here, when I say this was the coordinate of projection in terms of U, all you have to do is take U transpose X as your Neve data matrix. Here is the example you will understand better. Okay. So we are making the height measurements of people, inches and centimeters, but when you convert from inches to centimeters, there may be noise, right? Measurement noise. So we want to find the best subspace. For example, here, this line or this line, which one is best? Well, if I do blue line, look at the variance of data. See, the data is spread away, right? The variance. But if I project them into the red one, if I project them on the red one, you see the purple ones, the variation didn't kept properly because the data points came too close to each other. So the blue one is better than red one, right? So we'll find the best blue one. Okay. But there's a trick, we need to start with normalized data. Normalized data means each column has mean 0 and variance 0. I'm going to skip that part, but believe me that the data needs to be normalized. Normalization is an extremely simple process. What you do here is our data matrix. 10 inches is supposed to be 2.25 centimeters, right? But by measurement error, it's 28, and things like that. So these are my original data points. And I know that that's a line. So I know that I shouldn't work in R2. I should work in R1, right? But I need to find W bar. So how am I going to do it? First, I'm going to normalize my data. This part, I'm going to skip normalization. Just each column will be mean 0 and variance 1. And you can go to PowerPoint slides, and it's very easy. But let's go here. So this is my normalized data matrix. Okay? So what is the dimension? 2 by 6. That means I have 6 data points, and each one is in R2. But I want to still have 6 data points, but in R1, right? Very good. So here, I will compute SVD. This is my U when I compute SVD. What am I going to do? I will take U1, right? The first column. That's my U tilde. And then I will say U tilde dot W. I get this one, right? That's it. I'm no longer going to work with W. I will work with W bar. They are equivalent problems. Do you see? I reduced the dimension. But I have some more examples, very, very simple. So look at this. What do you see? My W is, this is normalized data, by the way. So I normalize it for you so life is easy. What is the dimension of data? 4 by 10, right? But if you don't know the dimension of the data, right? What am I supposed to do now? SVD. Okay, let's do SVD. Okay, what do you see? Well, 4. But look closely. What do you see? You see 5.5, 3.3, all of a sudden 10 times. So that means this data actually comes from two-dimensional subspace, right? Okay, that means I'm going to project into two-dimensional space, subspace. Because from 3.3 to 0.34, there's a sharp decline, right? So it is something like this. I have one singular volley, I have another one, boom, I have another one. It is like this, right? This is 5.5, 3 point, what is it? 3.3, then 0.34. So rank estimation algorithm, but visually I made it simple for you, okay? So now you're gonna say, oh, okay, all right, life is easy now. I'm gonna go and find you, but I have 4 columns. I'm gonna take only what? 2. That's it. That's my U tilde. And then I'm gonna project how U tilde times W. You see, I started with 4 by 10. I ended up with what? 2 by 10. That's it. You work with two-dimensional space now. Now let's make one last slide, last example. You see how easy it is? W. What is the size? You tell me. No, 8 by 10, right? Okay, what the heck is this? We don't know. What am I supposed to do? SVD. Tim is the magic guy, right? So always remember Tim. So look at this and tell me what you see. Rank is 3. So I don't need to work in 10 dimension. I need to work in 3 dimension. And how am I going to do it? Find U first. Okay. What is, oops. Oh, yeah, next slide. And find U, and then I will take the first 3 columns of U, and then I will project it, U tilde W. You see, from 8 by 10, I am now 3 by 10. Do you see simple? I know we sound cool with all those stuff, but very simple linear algebra. So now this morning you understand, I guess, how we project data from high dimensional space to lower dimensional space. You know what neural networks does? We from one node to another node, right? It takes data and geometrically change the data from one form to another form. But tomorrow morning, when we talk about CNN, for example, we will have hands-on. I didn't see the need for hands-on here because you can see it. So, and then this afternoon, we are going to have lunch now, upstairs, by the way, lunch. And then we'll come back at 1:30. We'll have some calculus. And after today, you will be ready for CNN mathematics tomorrow, which will be real good. And then there will be hands-on building session, and then afternoon, transformers. All right, that's all. Let's go have lunch, okay?
Only for the